Welcome to another video. In this video, we cover the properties of least squares estimators in simple linear regression and discuss how these properties are used to construct confidence intervals for the regression coefficients. We will also explain the differences between confidence intervals and prediction intervals and show how each is defined and interpreted. Up to this point, we focused on how to compute these least squares estimators and how to interpret them. Now we turn to understanding their behavior as random quantities. Because the regression coefficients are computed from sample data, they are themselves random variables. This means they have properties such as an expected value and a variance. Under the standard assumptions of simple linear regression, including linearity, independence, constant variance, and normally distributed errors, the least squares estimators have very desirable statistical properties. In particular, the estimator for the intercept and the slope are unbiased, meaning that, on average across repeated samples, they recover the true underlying parameter values. In addition, we can explicitly describe how much variability these estimators have, which allows us to quantify uncertainty, construct confidence intervals, and perform hypothesis tests. The standard error is simply the square root of the variance, but it plays a more practical role. While variance is measured in squared units and is harder to interpret, the standard error is expressed in the same units as the estimator itself, making it easier to understand and use. The standard error is what appears in regression output and is used directly to construct confidence intervals and perform hypothesis tests. To define a two-sided confidence interval, we can rely on the same t-statistic used to perform hypothesis testing on beta 1. We know that this statistic follows a t-distribution with n-2 degrees of freedom. From the properties of the t-distribution, we can state that the probability of this t-random variable falling between the negative and positive critical values corresponding to 1 minus half alpha is 1 minus alpha. Next, we replace the generic t-random variable with the t-statistic for the slope. From there, we algebraically manipulate the resulting inequalities to isolate beta 1 in the center and express lower and upper bounds in terms of quantities we can compute. These steps include multiplying all sides of the inequality by the standard error of beta 1, multiplying by negative 1, and reversing the inequality signs, and finally adding beta 1 hat to all sides. After completing these steps, we obtain a probability statement showing that beta 1 lies between beta 1 hat minus and beta 1 hat plus the critical t-value corresponding to 1 minus half alpha, with then minus 2 degrees of freedom times the standard error of beta 1, with probability 1 minus alpha. As a result, the two-sided confidence interval for beta 1 is given by beta 1 hat plus minus the critical t-value times the standard error of beta 1. This confidence interval gives a range of plausible values for the true slope, beta 1. It means for any alpha, for example alpha of 5%, if we were to repeat the experiment many times and construct the interval in the same way, approximately 95% of those intervals would contain the true slope. Similarly, we can derive a two-sided confidence interval around the intercept, beta 0. Returning to our example, we consider a chemist who is producing oxygen through a complex chemical process. Based on 20 experimental runs that have already been conducted, the chemist knows that the purity of the oxygen produced depends on the level of hydrocarbon present in the raw material. Our goal is to define confidence intervals around the coefficients of the fitted regression line. Looking at the results on the right, we see that in addition to reporting the estimated values of beta 0 hat and beta 1 hat in the coefficient column, Python also reports the standard errors of the least squares estimators, performs hypothesis tests on the significance of the coefficients, and constructs 95% confidence intervals for both the intercept and the slope by default. Interestingly, we can compute these confidence intervals ourselves using only the estimated coefficients and their corresponding standard errors. For the intercept, beta 0, the confidence interval is obtained by subtracting and adding the product of the critical t-value corresponding to 0.975 and 18 degrees of freedom and the standard error of beta 0 from and to beta 0 hat, respectively, to form the lower and upper bounds. Similarly, for the slope, beta 1, we subtract and add the product of the same critical t-value and the standard error of beta 1 from and to beta 1 hat to obtain the lower and upper bounds of the confidence interval. A confidence interval on the mean response describes the range of plausible values for the average value of the response variable at a specific value of the predictor. In other words, instead of predicting a single outcome, we are estimating the expected response for all observations that share the same predictor value. In simple linear regression, the estimated mean response at a given value of the predictor is obtained by plugging that value into the fitted regression line. However, because the intercept and slope are estimated from sample data, this mean response estimate is subject to uncertainty. A confidence interval on the mean response quantifies that uncertainty. This interval is constructed using the estimated mean response, the standard error of the mean response, and a critical value from the t-distribution with n-2 degrees of freedom. The standard error of the mean response depends on three factors: the variability of the data around the regression line, how far the predictor value is from its average, and the total variability in the predictor values. As a result, confidence intervals are narrowest near the average value of the predictor and widen as we move farther away from it. It is important to emphasize that a confidence interval on the mean response applies to the average outcome, not to individual future observations. It tells us where the true regression line is likely to lie at a given predictor value, rather than where a single data point might fall. This code computes confidence intervals for the mean response in a simple linear regression model using Python's stats models library. First, we specify the value of alpha as 0.05. This corresponds to constructing 95% confidence intervals. Next, we use the fitted linear regression model and call the get_prediction method on the matrix x_train_set. This method generates predictions at the observed predictor values. By calling summary_frame, alpha, we obtain a table that includes the predicted mean response as well as the lower and upper bounds of the confidence interval for the mean response at each x value. We then create an empty pandas data frame called confidence, which we use to organize the results in a clear and readable format. The next two lines copy the original data into this new table. The column labeled hydro stores the hydrocarbon levels, and the column labeled purity observed stores the observed oxygen purity values from the dataset. We then add the predicted mean response from the regression model to the table, using the column labeled mean from the prediction summary. This represents the estimated average oxygen purity at each hydrocarbon level. Finally, we add two more columns that contain the lower and upper confidence bounds for the mean response. These come from the mean_ci_lower and mean_ci_upper columns of the prediction summary. The final output is a table that, for each hydrocarbon level, shows the observed purity, the predicted mean purity, and the corresponding confidence interval for the mean response. This allows us to visually and numerically compare observed data points with the uncertainty around the estimated regression line. A prediction interval is used when our goal is to predict the value of a single new observation of the response variable at a given value of the predictor. Unlike a confidence interval, which describes uncertainty in the mean response, a prediction interval accounts for both the uncertainty in estimating the regression line and the natural variability of individual observations around that line. In simple linear regression, even if we knew the true regression line exactly, individual observations would still vary due to random error. A prediction interval captures this additional source of uncertainty, which is why it is always wider than the confidence interval for the mean response at the same predictor value. Prediction intervals are constructed using the predicted value from the regression model, a critical value from the t-distribution with n-2 degrees of freedom, and a standard error that includes the error variance of the model. This ensures that the interval reflects both estimation uncertainty and observation level noise. In practical terms, a prediction interval provides a range in which we expect a future oxygen purity measurement to fall for a given hydrocarbon level with a specified level of confidence, such as 95%. Further expanding our previous table to include the prediction interval, we add two additional columns that provide the lower and upper bounds for predicting a new individual oxygen purity value at each hydrocarbon level. As expected, these prediction intervals are wider than the confidence intervals for the mean response because they account for both model uncertainty and random variation in new observations. Thank you for watching. I hope this video was helpful, and I look forward to seeing you in the next one.